Welcome to the AP presentation on solutions. This is not all of the information that you'll learn on solutions in this course, but it is a primer of information that you will need in order to proceed to future units. So, first things first, the learning goals is you should be able to understand the properties of the atom that allow for a solution to dissolve. You should be able to calculate the molarity and molality for solutions, including dilutions. You should be able to name and calculate the pH of strong acids and bases. You should be able to recognize and balance oxidation reduction reactions, and you should be able to assign oxidation numbers. So, properties of solutions. A couple of things. First year chemistry. A solute is a substance that's dissolved in a solvent. A solvent is something that dissolves a solute. So they're kind of two sides of the same coin. Generally speaking, the solute is the one there is less of, and the solvent is the something that there is more of. That's kind of a general rule. So for example, if you mix salt and water, the salt is the solute, the solvent is the water. So we have the rule that like dissolves like. So polar solutes will dissolve in polar solvents. So something like water, which is a polar solvent, will dissolve things because of the whole idea of the partial positive and partial negative charges. Those partial positives and partial negative charges right there allow them to break up ionic compounds, or they allow them to arrange such a way where water molecules intersperse themselves in other polar substances. So for example, if you have sodium chloride, sodium chloride will dissociate into sodium ions, which are attracted to the oxygens, and chlorines will go to the hydrogen side because hydrogen has a partial positive charge. So that's what we mean by when we talk about dissolving something. Something else to keep in mind is that nonpolar solutes will dissolve in nonpolar solvents. The most common nonpolar solvent that we generally hear about is benzene. Benzene is the whole 1,3,5 dicyclohexane. Okay, it's the alternating double bonds. This is the most common nonpolar solvent that we generally see. Electrolytes. Electrolytes are something that will break up into solution and form ions. So generally speaking, when we talk about electrolytes, we're referring to ionic substances. Ionic substances, whenever you put them in water, will separate into positive ions and negative ions. Well, because of that, this particular property will actually allow them to conduct electricity. So since they conduct electricity, they're called electrolytes. One common thing that you see for electrolytes is you actually see Gatorade. Gatorade actually advertises itself as it has electrolytes. Well, that's just another way of saying that it has salt. Disassociation, so ionic compounds can, and in fact they will, disassociate in water. And here you see the sodium ions and the chlorine ions separating like we talked about, and you can see how the water molecules arrange themselves around those positive and negative ions. So whenever you have electrolytes in solution, you can see right here, this is an example where you have water, and then you have two electrodes that have an electrical current that would like to go between them. But by putting them in a solution with positive and negative ions, it actually allows these ions to migrate to one side or the other and allow an electrical current to conduct through the water. Now, traditional water, regular water, just H2O, is not a good conductor of electricity. However, when you start to do things like dissolve salts in them, water, especially if it has salt dissolved in it, is a very good conductor of electricity. The strength of an electrolyte, or how completely it disassociates, can be determined using something called the solubility product. And that's what we see here, the solubility product constant. So anytime you see a K value, that generally means a constant. This SP stands for the solubility product part of this. Now what happens is you can actually have a substance that you can say dissolves. In other words, AB, which is a solid, think of this as sodium chloride, will go into sodium plus chlorine in an aqueous solution. You can actually measure the degree to which this happens. Not all sodium chlorides would necessarily come apart in the solution. So what you do is you just write the equation. So since there's no coefficient here, there's a 1, and there's no coefficient here, that's a 1, I can write what's called a KSP expression as Na plus Cl minus. Now this is going to become particularly useful whenever we start to talk about what happens if I mix sodium chloride and sodium sulfate. Well, how many of each ion are there in solution? You're going to have to look at it from the perspective of there's multiple things contributing sodium ions. So as an example, it says a hair dryer falling into the bathtub is a hazard often seen in movies. Would replacing the water with the ionized distilled water make the bath water safe? Justify your answer. So there's kind of a two-pronged answer here. The first one is that obviously yes, it would actually make it much safer because whenever you have deionized or distilled water, it does not conduct electricity. However, what you're failing to neglect is whenever you have your body itself has salts that are on the surface. In fact, sweat has salt in it as well. So just by the mere fact that you get into this bath water, you would actually salinate the water. Okay, you'd put salt in it, and then therefore it would be able to conduct electricity. It does not take a lot of salt to be able to conduct electricity. So although our initial answer is it makes it safe before we get in the tub, the real answer is no, it's not okay to have distilled water and then drop the hairdryer in a bathtub. The proficient level question says the human body requires both aqueous solutions and essential oils to function. A cell membrane consists of a hydrophobic and hydrophilic parts. Describe where each will be relative to the cell membrane. So whenever you have a hydrophilic substance, what that means is that it really likes water. If it really likes water, this actually right here is the positive or charged part of a particular cell wall. It can be positive or negatively charged. Okay, and then right here, the hydrophobic parts. These hydrophobic parts, they don't like water, they fear water, they don't really fear it, and that consists of your hydrocarbons. So things like CH3, CH2, CH3 is an example of something that is a nonpolar substance and would tend to go in with the hydrophobic parts of the membrane. Next it says the solubility product constant of PbCl2 is 1.6 times 10 to the minus fifth. So this right here is the value of KSP. And we actually want to know how much solution there, or excuse me, how much of each solution, or lead primarily, but how much of each there is in solution. So we need to start off by writing what's called the KSP expression. So we would say PbCl2 would go to Pb2 plus 2Cl minus. Okay, that right there is how it will disassociate. So when I'm writing my KSP expression, I would say KSP is equal to Pb2 plus and then times Cl minus, and then we can square that value. Now the reason why we have to square the Cl minus is because it has a coefficient this time. If you look back at our original version, it was a to the eighth and b to the bth. So since we have this right here, there's an expression right there. Now another way that we can look at this is say, originally if I have x PbCl2s, whenever it disassociates, if it were to disassociate completely, or if x number of molecules were to disassociate, I would have x Pb2 pluses, right? I would have one for each one that fell apart. However, if I were to do it with chlorine, I would have 2x. Because for each x that falls apart, I produce 2 chlorines. Now don't forget, this chlorine term, the 2x term, is squared. So actually what we end up with is a term 4x cubed. And the reason why I end up with that is because 2x is a squared term. So that becomes 4x squared times x is 4x cubed. Now remember, this right here equals the KSP expression, which I've already identified. The KSP expression is 1.6 times 10 to the minus fifth. 1.6 times 10 to the minus fifth. At that point, you can now solve this mathematically. You would divide both sides by 4, and then after you did that, you would take the cube root of that number. Whenever you take the cube root of that number, you actually end up with a number that's like 1.59 times 10 to the minus second. Now that right there is my x value. Now remember, x in our case is the lead concentration. So I can say that this is the molarity of lead. Now if I was looking for the molarity of chloride ions, I would have to take this number and multiply it by 2. Because remember, chloride ions were 2x, not x. Now, these KSP expressions are pretty important. You're going to have to know how to do these, especially when we talk about equilibrium and we talk about how fast reactions go. You need to have these KSP expressions down pretty pat. Now, whenever you're talking about a solution, there's multiple ways to express the concentration, but the most common ones are molarity and molality. Now, molarity is the number of solute particles dissolved per liter of solvent. Generally speaking, we would calculate the molarity as moles over liters. The molality is very similar, but the molality would be molality, and molality is generally kind of a lowercase script m, is equal to moles divided by kilograms of solvent. Now, a lot of times, these are the same number, especially when we're talking about something that's dissolved in water, because 1 liter of water is 1 kilogram of water. However, there are certain circumstances when it makes much more sense to use molality. Like, for example, whenever you're heating a substance up, or you're trying to find a boiling temperature as you're adding salt. The reason why is, whenever you heat something up, the volume will expand. So just by heating a substance up, you're actually changing the molarity. But the molality will remain constant. Even though it expands, the same amount of particles are still there. So you see those expressions right here. We say molarity, moles over volume, molality, moles over mass. And so generally speaking, you see your kind of cursive M, and here you see your capital M to express molarity and molality. Ionic molarity. Ionic molarity is the way of expressing how many ions are in solution. For example, whenever you have 1 mole of barium chloride, you have 2.0 moles of chloride ions. Now this is assuming, and it's making the assumption that this thing disassociates completely. It may not. We haven't looked at any of the KSP expressions. But if this thing were to disassociate completely, I would have 2 moles of barium chloride. In addition to that, I would have 1 mole of Ba2+. Now if I would ask you for the overall ionic molarity, the overall ionic molarity would be there are 3 moles of ions, or 3 molarity of ions. Now generally speaking, we don't look at that because that's not really something we're interested in, but you will be asked to look at individual molarities for ions. So you see right here it says calculate the mass of iron phosphate necessary to make a 0.5 molar solution. So we've done this a lot in the labs, but now we're officially covering it in the presentation. And it says, okay, I need to make this. So what I need is 0.5 moles per 1 liter. But I don't need 1 liter of solution. Instead, what I need is 250 mils. So I would say 1 liter is 1,000 milliliters, and then I'd multiply it by 250 mils. When I do that, that would give me the number of moles that I need. But remember, we're not stopping there at how many moles we need. So we're going to go ahead and continue this thing on. If we were to continue this thing on, the next thing I would do is I would say, okay, 1 mole of iron 2-phosphate, and I can actually look up the molar mass. The molar mass is about 357.48. And the reason why I know that is I can actually write out iron 2-phosphate. When you have iron phosphate and you have to make the charges balance, remember this is a 3- charge, this is a 2+ charge. So you have to have iron 3, phosphate 2 in order to get the charges to balance. Once the charges balance, you can look at your molar mass. And the molar mass is 357.48. Once you do that, we now have liters is canceled, milliliters is canceled, milliliters is canceled, moles is canceled, moles is canceled. The only thing that's left is grams. And in fact, when you measure this out, or whenever you calculate it out, you should get something like 44.685 grams of iron 2, but there's 3 of them, phosphate. Okay, that right there is how many grams are necessary to make 250 mils of 0.5 molar solution. Now that's something you should be very familiar with from the lab, but you should also be familiar with it for tests now as well. B2 example, it says what is the molality, which is going to be different. Remember, molality is moles per kilogram of copper sulfate dissolved in 2 liters of DMSO. So the first thing I want to do is I want to say I have 100 grams of copper sulfate, and I can take that 100 grams of copper sulfate and I can divide it by 2 liters of DMSO. And most people get off to the right start here. They say, okay, I've got copper sulfate. The molar mass of copper sulfate is 159.6 using the periodic table. So that's 1 mole. But then they stop there. The problem is, if they stop there, you've calculated the molarity, not the molality. So in order to get it from molarity to molality, you need to continue on. You'd say, okay, in 1 liter, there is 1,000 milliliters. And in 1.1, in 1 milliliter, there is 1.1 grams. And then the last step you would have to do is you'd have to convert from grams back to kilograms. Now, one thing that you should see is that this milliliters and this grams calculation, they're going to cancel each other out. So if you have 1.1 grams per mil, that's the same thing as 1.1 kilograms per liter. So if you didn't know that, that's okay. Then you follow the instruction or the dimensional analysis as we go across. When you look, grams of copper sulfate is going to cross out with grams of copper sulfate. Liters of DMSO, liters, milliliters, grams, and grams. All I'm left with is moles per kilogram. Now when you multiply this across, you actually end up with something like 0.57, and then we express it like a lowercase script m, molality, copper sulfate. In the next question, it says, what is the molarity of lead if 150 grams of lead cyanide is dissolved into 500 mils of water? So we start off with the idea that we have 150 grams of lead cyanide. The first thing we need to do is we say, okay, that's 500 mils. And some of you probably abbreviated it as 0.5 liters, and that's good. You have 1,000 milliliters is 1 liter. And then now you keep going across. The next thing you would say is you'd have to find the molar mass of lead cyanide, and that's about 311.27 is 1 mole. So now once you multiply this across, you'll have your molarity, and we'll let you do that one on your own. Now, dilutions. It's not enough just to make a solution. Oftentimes we make or we have stock solutions, but the problem is that you need a solution that's a different concentration than what you have, or that you can feel comfortable making. So you need to be able to dilute existing solutions as well. Now we have covered this in the lab as well, but whenever you look at this, you need to be able to use this equation. Basically what this equation is saying is the molarity of the first one times the volume of the first one equals the molarity of the second one times the volume of the second one. This is just another way of saying that the number of atoms are conserved. Okay, when you take molarity and you multiply it by volume, you get moles. So you have the same number of moles when you add water, is basically what this thing is saying. So an example of this would be, given a 2.0 molar stock solution, how can you produce 50 mils of 2 times 10 to the minus 6th molarity? So the first thing we want to do is we want to look at it from the perspective of a dilution. So I have 2 molar stock solution. I don't know how much I'm going to put in, but I know that I want to get 2 times 10 to the minus 6 molarity out, and I want 50 mils of it. So I guess I'm saying, how much of this original solution do I need in order to make this occur? So when you do this, you would divide both sides by 2, and then you'd multiply everything out. And when you do that, you end up with a very, very, very small volume. The volume ends up being like 5 times 10 to the minus 5th milliliters. So you're talking about 500 thousandths of a milliliter, something like that. Well, at this point, that's not a workable solution. You cannot get that small of a volume to any degree of accuracy. So instead, really what you'd want to do is you'd want to do the procedure that you see here. You'd want to take a 2 molar solution. And when you see the 2 molar solution that you see here, you'd say, okay, I'm going to take 1 mil of this. And when I take 1 mil of it, it's going to go from 2 molar to 0.2 molar. And the reason why is I'm doing a 1 to 10 dilution. In other words, I have 2 times 1 equals, I'm trying to solve for the concentration, and then a total volume of 10. Remember, this stands for the total volume, 9 plus the 1. So right here you can see right away that you're just basically taking your original solution and dividing it by 10. So each step along the way does it by 10. So it goes 0.2, 0.02, 0.002, 0.002, and so on and so on and so on. Now in order to get to this 2 times 10 to the minus 6 concentration, you have to do this procedure 2 more times than is shown here. But this is a workable solution. You can actually take this and get to that low of a concentration using this particular method. This is called a serial dilution procedure. Next, we see you are given 250 mils of 1 molar HCl. Unfortunately, this investigation you are attempting to complete requires 4.5 molar acid. How can you reverse dilute the sample? So let's look at it just from the equation perspective to begin with. So if you were to look at it, I have 1 molar solution, I have 250 mils of it, it equals 4.5, and then some sort of volume change right there. From a purely mathematical perspective, if I take this and divide it out, I end up getting a volume of about 55.6. So now the question arises, okay, it's at 250 mils, how can I get it to be 55.6? And the answer is, you would take it and you would evaporate some of the solution off. The water would be the thing that would be leaving the HCl to concentrate in the flask below. So this is an example of how you can do a reverse dilution, which we're going to call concentrating the sample, by just evaporating off some of the water. This is particularly useful, especially when you're working with solutions that contain salts, like sodium chloride or copper sulfate, because of the high boiling point of, the high boiling point of those salts due to intermolecular forces. Precipitate. So the precipitate is where you mix 2 solutions. So I have solutions and solutions, you mix them together, and all of a sudden there's a precipitate at the bottom. The precipitate is an insoluble solid. Okay, insoluble solid means if these for whatever reason are water, this right here is going to precipitate out. That means it's just not going to dissolve in water. So this is what we call a precipitate reaction. It's also sometimes called a metathesis reaction. Okay, you guys probably learned them as double replacement reactions last year. Now there are certain rules that govern solubility, and these are things that you have to memorize. So you have to memorize, and that's why you have Dwight here saying you got to memorize. Okay, it says group 1 and NH4 cations are soluble. Anything that you attach to a group 1 element is going to be soluble. Okay, so it doesn't matter if it's sodium chloride or sodium cyanide or sodium phosphate. It doesn't matter. If you've attached a group 1 element to it, it is a soluble. Next, it says acetates, which you should know is CH3COO, are nitrates, NO3s. Perchlorates, ClO4s, are soluble as well. Okay, bromines, chlorides, and iodides are also generally soluble. Sulfates are soluble except when they're formed with calcium, strontium, and barium. Salts containing lead, mercury, and silver are insoluble. There are some exceptions to that. So, like for example, silver is soluble when you pair it with chloride. And we'll work through some of those exceptions here in a little bit. But carbonates, phosphates, sulfides, and oxides and hydroxides are generally insoluble as well, except when you have these rules here. So these are the general rules regarding solubility. But once again, you need to understand that we don't really talk about things in terms of absolutes. Just like we said, something's not really ionic, it's not really nonpolar, it's on a continuum. It's the same thing with solubility. Okay, it's not that something is insoluble, it's that very little of it is soluble. So you have things that are very soluble, and that doesn't mean they all fall apart. And you have things that are insoluble, and that doesn't necessarily mean that none of them dissolve. So you have to realize that it's a continuum that you're looking at. And that's why we look at the KSP expression in AP Chemistry. So this is the metathesis reaction process, okay, also known as double replacement. The first thing you need to do is you need to identify the ions, you need to write the product, and you need to check the solubility. So you'll be given something like this, AX plus BY. To check and see if this reaction is feasible, all you would do is replace A and B. Okay, that's why it's called a double replacement reaction. So when we take that, you've got AY plus BX. Once you've balanced the equation and everything, the first thing you need to do is check solubility. In order for this metathesis reaction to occur, one of these two products, one of these must be insoluble. If it is soluble, if both products are soluble, this reaction will not occur. Not work. Okay? If one of the products is insoluble, it will work. If both of the products are soluble, it will work. But you have to have at least one product be insoluble. We can create what's called a net ionic equation, and this might help you actually understand the reason why one of the products has to be insoluble. So generally we write a reaction like calcium sulfate plus barium nitrate. And everybody looks at that, we know what this is, we can look at the equation and understand it generally. But we need to look at it in terms of the ions. Remember, when you put calcium sulfate in water, it's not really calcium sulfate anymore. It's calcium ions and sulfate ions. It's not really barium nitrate. It's barium ions and nitrate ions when you put them in water. So now you have to look at these ions and say, okay, are there any ways that these ions, when they attach, will become insoluble? And that is, it does happen when you mix barium with sulfate. When barium attaches to sulfate, the product becomes a solid and is no longer aqueous. At that point, those ions are no longer in solution. Okay? Once those ions are no longer in solution, we don't write them as ions, we write them as a solid product. But there still are ions left over, calcium and nitrate. So now we make what's called a net ionic equation. So I had ions on the left, I do have some ions on the right. The ions on the left and the ions on the right will cancel out, and they will give you what's called a net ionic equation. Write a net ionic equation for silver chloride reacting with potassium sulfate. So if you were to do this, you start off with the idea of silver chloride, which is AgCl plus potassium sulfide is going to be KSO4. We need to balance the charges. Now, the potential products that we have are silver sulfate. Now, if I were to do that, I'd have to put a 2 there. Plus, the other potential product that we'd have is KCl. Now, this doesn't balance. I need to balance the equation by putting a 2 there. Once I put a 2 there and a 2 there, now I have a balanced equation. The problem with this is we need to look at it from a whole perspective. Will this reaction occur? And yes, it will, because this product right here is insoluble. Because of that, this reaction will occur. Since this is an insoluble product, that means I'm going to have it at the end of a net ionic equation. So these potassium right here are ions, but so are these. So those are going to cross out, and they're going to be on both sides. The chlorine ions the same way. They're going to cross out, they're going to be on both sides. So the net ionic equation that we would have here is 2 Ag plus SO4 2 minus goes to Ag2 SO4. Now the next one says write a complete ionic equation for the aqueous copper reacting with silver sulfate. So we'd say, okay, I've got aqueous copper, which means it's just copper by itself. We'll say it's 2 plus, is reacting with silver sulfate. Silver sulfate. If we were to do this, you can actually write this thing out and say, okay, CuSO4 plus Ag. The problem with this is none of these products are insoluble. Okay, silver can exist by itself, and it is an ion in solution. Copper sulfate is dissolvable. You can dissolve copper sulfate in solution. We've done that tons of times to make a blue solution. So because of that, you cannot write a net ionic equation for this because there are no products. So no reaction. And that is a perfectly justifiable answer. No reaction when somebody says to write a net ionic equation. Acids. Okay, there are 2 different types of acids, or 3 different types of acids we need to talk about. The arrhenius acid is where you increase the amount of hydrogens when water is added. So for example, you have HA, you add water, you get aqueous hydrogen ions and aqueous A- ions. So that right there is an example of an arrhenius acid. Okay, arrhenius acids are the general definition that we're going to work with, but you do need to understand the Bronsted-Lowry definition for an acid, and the Lewis definition for an acid. You need to know both of those as well. So the first thing we need to really look at is you need to look at the idea of what is a Bronsted-Lowry acid. A Bronsted-Lowry acid is where something actually takes its and it donates its proton. This right here is a Bronsted-Lowry acid because it gives its proton to something else. Not just there's a free proton, but it's actually giving its proton to water. That actually makes you have H3O+, which is called a hydronium ion, and A-. Now this right here is the same thing as this. Aqueous hydrogen ions is the same thing as H3O+. But there are certain substances that are Arrhenius acids are Bronsted-Lowry acids or Arrhenius acids. Generally speaking, if something is a Bronsted-Lowry acid, then it generally is an Arrhenius acid. Okay, but there is a continuum. Arrhenius acids and Lewis acids. Lewis starts at the top, then it goes to Bronsted-Lowry, then it goes to Arrhenius, with Arrhenius being the most specific definition. There are certain substances that will donate protons, but when you put them in water, will not have free protons. So it makes a big difference when we're talking about the definitions. The next one would be the idea of a Bronsted-Lowry acid. A Bronsted-Lowry acid is something when it deals with electrons. So you have something like HA, and that's something like that would be more like a chlorine ion. So you have like HCl. What happens is you have something that has the ability to accept electrons. So remember, water has two sets of free electrons. If it donates its electrons to A can give its electrons to something else. Whenever you do that, you can create what's called a Lewis acid. So Bronsted-Lowry donates protons. Lewis acids accept electrons. I'm sorry, I should have drawn this to the H and then kicked the electrons off. Sorry, I didn't mean to confuse you there. Naming acids. We've already covered the rules for naming acids. If it is an 8 ion, it becomes an ic. So sulfate becomes sulfuric acid. And so on and so on and so on. If it's an ite ion, it's an us. If it's an ide, which is all elements by themselves, like sulfide, becomes hydrosulfic acid or hydrosulfuric acid. Now, generally speaking, we measure the strength of an acid by the amount by how easily it disassociates its proton. Okay, so we've probably calculated the pH before, but pH is equal to the negative log of the hydronium concentration, or the hydrogen ion concentration. The stronger the acid, the lower the pH. Now, just so you know, you can have a pH less than 0. That is a possibility. Now, generally speaking, we'd have to manipulate some things for that to occur, but you can have, and we will work with solutions with a pH below 0. Okay, a pH is representing how strong an acid is. Whenever you look at things like battery acids, you see things that are very low, like 0.5. Now, something ceases to be an acid when it crosses the pure water threshold. Pure water is at 7.0. Once you cross that pure water threshold, you are no longer an acid. Instead, you cross the realm to a base. Bases are things that have more hydroxide ion concentration, and we will talk about that in a little bit. You do need to know about acid dissociation. Things that are strong acids dissociate 100% when a 1 molar solution is put in standard conditions. So here are the strong acids. You need to memorize these because you need to be able to recall them very quickly. You have perchloric acid, okay, because you have a pure perchlorate ion, chloric acid, hydrochloric acid, sulfuric acid, hydroiodic acid, and nitric acid. These are the ones that are generally considered to be the strong acids. Okay, some people also include HBr, which is hydrobromic acid, and you should include that in your memorization as well. These are the acids that dissociate 100% at 1 molar. Now, for the purposes of this presentation, we're just interested in you identifying whether something is a weak or a strong acid at this point. Later this year, we will get into weak acids and how to tell pH of weak acids. Okay. Next, we have bases. We've already talked briefly about bases. Bases are basically the opposite of acids. So an Arrhenius base doesn't increase the amount of hydronium, it actually increases the amount of hydroxide whenever you add it to water. That's the Arrhenius definition for a base. A Bronsted-Lowry base is no longer defined as something that accepts a proton. It should be something, or excuse me, it should be something that accepts a proton, not something that donates a proton. So for example, when we have our example here of BOH, okay, what is exactly accepting the proton at this point? And it's actually this substance right here, this BOH, is accepting this proton from the water molecule, and then you're going to have these two OHs that are there. So the Bronsted-Lowry base is the same thing. It's something that can accept the proton as opposed to donating the proton. And the last thing that you have is the Lewis base. The Lewis base is something that can donate electrons to something else. Okay, you need to once again know the definitions get more specific, with Lewis being very broad and Arrhenius being very narrow. Base strength. So we've talked about pH. There is also pOH. In fact, anytime you see a P in front of something like that, it means take the negative log. So I could ask you for what's the pKsP, and you should be able to tell me what that is for a particular substance. You just take the KsP and take the negative log of it. So whenever you look at these things, you would say, okay, once I cross 7, I'm now into the base territory. This is on the pH scale. Now, generally speaking, you also have a pOH scale. Now, the two are related, and we're going to talk about that in just a second. But when you have a pOH that is low, it is a strong base. Now, everything that's listed here is in the pH scale. So when you see something like bleach and go, well, bleach must not be very basic, it is very basic. Once you cross 7 for the pH scale, you're a base, and then you would also decrease in your pOH. The base dissociation constant, you can write a KB expression just like we did for KSP. It's just done with bases as opposed to acids or salts. You do need to memorize the strong bases as well. Now, the strong bases are a little bit easier to memorize just because it's basically everything in group 1 and group 2. Now, it's not everything in group 2, and in fact, you see some issues here. It should be calcium hydroxide right there. But it's most of the things in group 2 and everything in group 1. You do need to memorize these because you do need to be able to say whether or not something is completely disassociated. Now, you can relate pH and pOH to each other, and the reason why these things are related to each other is based on the autoionization of water. Water itself will disassociate into hydronium and hydroxide ions, but it does so at a very, very small concentration. Okay, it happens at a molarity of about 1 times 10 to the minus 7th. So it turns out that whenever you take the negative log of that, you actually get the value of 7, which is where water gets its pH value of 7 from. If you were to look at and solve for each concentration there, you'd have 1 times 10 to the minus 7th for each. So whenever you add those two things together, that's why we get the idea of the pH of 14. So pH plus pOH, because remember I take the negative log of this and the negative log of that, P and P would end up being 14. These right here are indicators. You do not have to memorize indicators, but you do need to know how to use a table of indicators, or what sort of indicator you would use for a particular problem. Indicators are great because they'll actually change color when you get to a certain pH range. So something could be red initially, and then as you add base to it, it'll turn yellow, and then green, and then blue, and then violet, and then back to red. So these indicators are really useful whenever you don't have something like a pH probe available. Here, developing E1 says, write a balanced chemical equation showing the neutralization of phosphoric acid with sodium hydroxide. So this is just another way of checking to see whether or not you know naming or writing chemical reactions. So we write sodium hydroxide, which is NaOH. We're going to add phosphoric acid. Phosphoric acid is H3PO4, and it's going to go to, we have to do kind of a double replacement or a metathesis reaction at this point, but it's a neutralization. So we would see NaPO4 plus H2O. Now, what we have to do is we have to write a balanced chemical reaction. So if you look at it, we're not balanced right away. In fact, this wouldn't possibly be a product. It'd have to be Na3PO4 because phosphate has a negative charge. So once you see that you need 3 sodiums, you need 3 of these, which would then in turn produce 3 waters. So you see an example of a balanced neutralization equation. Next it says write a solubility of product constant for the dissociation of acetic acid. Now when we have acetic acid, this right here is acetic acid. Now, for some reason, they always draw the H at the end for acetic acid. It's more of an organic chemistry sort of function than anything. Basically, what you have is it breaks into CH3COO plus H plus. Now, when you rewrite this Ka expression, which is really what it is, because it's the dissociation of an acid, you would get CH3COO minus H plus over CH3COOH. This right here is a solubility product constant definition for the dissociation of acetic acid in a solution. Just so you know, when we come back to this later in the year, you'll have to at this point solve for the H and then calculate the pH based on this. The reason why a solubility product or a dissociation constant is necessary at this point is because acetic acid is not a strong acid. So you'd want to measure how much of it actually falls apart. The next example says calculate the pH of a solution of 1 molar of calcium hydroxide. So calcium hydroxide, we have to look at it and we say, okay, if I have a calcium hydroxide that falls apart, for every one of these that falls apart, it's going to produce 2 hydroxide ions. So if I have a solution that's 1 molar calcium hydroxide, that solution is going to be 2 molar hydroxide concentration. That's what I need to know as far as trying to figure things out from here. I can calculate the pOH. The pOH is the negative log of the hydroxide concentration. Now the reason why I know it's 2 and not some other number is this right here represents a strong base, which means it's going to disassociate completely whenever we talk about it in terms of water. So I take the negative log of 2. The negative log of 2, whenever you put that into a calculator, ends up being a very, very strange number. You're going to get something like negative 0.30 is the pOH. Now remember, I told you it's okay to have the pH go below 0. It's the same thing with the pOH. At this point, you would need to relate the pOH to the pH. Remember, you can do that by saying pH plus pOH is equal to 14. When you plug in from there, you would say, okay, if the pOH is negative 0.3, that must mean the pH is 14.3, which is above 14 on our traditional scale, which is also okay. So this right here represents the pH of a strong base. Now I will tell you this much. Whenever you get into higher level chemistry courses, you'll study these a little bit more. They're called diprotic or dihydroxyl systems. It turns out that both hydroxyl groups don't disassociate completely, but that is well beyond the scope of this class. Next we have oxidation. Oxidation is something that loses an electron and is oxidized. So for an example, this is oil. Oxidation is losing electrons. Potassium in this case, you had a solid molecule. You had potassium, just metal potassium. Now all of a sudden it's aqueous, and so you have something that has lost electrons. I guess the better way to put this would probably be K solid plus Cl gas or something like that. And at that point you could clearly see that the potassium had an electron that was removed, so because of that, potassium is oxidized. Now, something is reduced if it gains electrons. So we say Rig, and we say oil rig. Oxidation is losing, reduction is gaining. So if you were to look at this, the chlorine had an electron added to it. So since it had an electron added to it, now you have the idea that it's been reduced. We refer to something as an oxidation reaction or a reduction reaction, but instead it's a combination of the two that we call a redox reaction. You can't have something be oxidized unless something else is reduced, because the electron has to go and come from somewhere. So we call these redox reactions. And what you see here is you see solid zinc and copper sulfate, and then all of a sudden on the other side you have zinc sulfate and copper solid. And what that means is the electron is being transferred from the zinc to the copper. Now this is a useful chemical reaction that we'll talk a little bit more about in electrochemistry, but you need to be able to identify something as being oxidized or reduced. This is particularly useful if we want to plate something with a metal, like something can be gold plated, or if we want to construct a battery. You can put two chemicals together that will encourage the electrons to move one way or the other. So this is a great unit as far as a practical and useful application of some of the chemistry concepts you've learned. Now, we also need to know about oxidation numbers when we start to look at these sort of reactions. And oxidation numbers are pretty easy to follow. The rules are that elements are always zero. If you have zinc and zinc is by itself, its oxidation number is zero because there's nothing wrong with its electron differential. There's no electrons missing or electrons that are there. Now, so the oxidation number of elements that are by themselves are always zero. Now that applies to diatomics as well. If you have H2, the oxidation number is zero because that's technically an element by itself. Next, you have monatomic ions. Monatomic ions have the same oxidation number as their most stable ionic charge. So lithium is always +1, calcium is always +2, boron is always +3, nitrogen, oxygen, fluorine, etc. Okay. There are a couple of rules regarding nonmetals, and the first is this. Fluorine is always -1. There are no exceptions for fluorine being -1. Other halogens are generally -1 unless they're bonded with oxygens. So the rule tends to go fluorine is always -1. If there is no fluorine, the next thing you do is you look at oxygen is -2. Okay. Once you've established that oxygen is -2, then you would look at the halogens. Are there any other chlorines or anything like that? Then you would look at hydrogen. Hydrogen is generally +1, but it can also be -1. Then you look at the other patterns that you see. So you would say, is there lithium? Something along those lines. Because you can have a substance like this. Lithium, +1, hydrogen, -1. You can have things like this. Oxygen, F6. Fluorine's always -1, which in this case makes oxygen +6. So the oxidation numbers for any particular substance have to add up to 0. And that's what we have here. You see the sum of the oxidation numbers add to 0. Okay, and you see Avogadro right there. Okay, next you have the activity series. Now the activity series is based on the ability to oxidize or reduce particular substances. And the activity series is also used to predict what we call single replacement reactions. Now you need to know the activity series, the general trends. You should know that lithium is at the top, that lithium is more reactive with anything than anything else. And the reason why is lithium ions are going to be more stable than lithium with a single valence electron. Okay, you should be able to relate this to effective nuclear charge in Coulomb's law. The higher something is on the activity series, the more likely it is to react with something else and take on a more stable version. At the bottom of the activity series, you see things like gold, platinum, mercury, silver, copper. All of those things right there are not likely to replace anything else in a reaction, and the reason for that is they are generally pretty stable. They have these overlapping D subshells. The D subshells is delocalized and therefore doesn't cause a lot of the issues that you see with S and P subshells. Example F1, it says find the oxidative state of sulfur in a sulfuric acid ion. Sulfuric acid. So we see H2SO4. Okay. The first thing we want to do is we want to look at sulfate. We know sulfate overall has a charge of -2. We know that there are oxygens, and our priority goes with oxygen. Oxygen is always -2 unless there's a fluorine. There's no fluorine in this case, so I'd say it's -2. There are 4 oxygens, which gives it a total charge of -8. Sulfur is generally -2, but instead, because of its position, is going to operate as a +6. There's one of them, and if you look at that, that adds up to our -2 charge that we see right here. So you can look at the oxidative state right there. Now, The hydrogens make this whole thing balance out to 0. So hydrogen has to have an oxidative state of 1 or plus 1, and there are 2 of them. So if you were to look at the oxidative state of each one of these atoms, it would be oxygen is -2, hydrogen is +1, and sulfur is +6. You should be able to do solution stoichiometry, which is basically saying you should be able to know how these things are going to react in solutions. So if you have this, you need to be able to convert that to moles. If you have this, you need to be able to convert that to moles. I would have to give you a concentration there. And then you should be able to say, okay, based on this, what's going to occur? So you should be able to work in solutions. In other words, take solutions to moles, and then go back moles to the reaction, and then the reaction back to moles, and then back to solutions again. And we'll get plenty of practice on that in class.